All right, welcome to our student session on robotics and control. Our first speaker will be Aadeel Akhtar. He's from the Neuroscience program at UIUC. The title of his talk will be The Future of Upper Limb Prosthetics. Thank you.
Thanks, Zaya. So again, I'm Aadeel Akhtar. I'm an MD PhD student here. I'm working in the laboratory of Tim Brettel. And we work on prosthetic devices. And so the first thing that I wanted to start off with was a video that they show, a commercial that the U of I made for the football games that they play on ESPN.
Can we fit him?
How did they do that?
What did you do? Where's the English building?
Could you go over that again?
Hey, can I check that?
When's that paper due?
Can I tell you my idea?
How can we make it cheaper?
Do you think this will work?
How did that feel? So what I want to kind of get into is, how do we get to that point? To the point where we can actually put these low-cost prosthetic devices on an amputee and have him control it just by when he thinks about flexing his hand, that the hand will flex. And so for me, the journey started when I was actually 7 years old, and I was visiting Pakistan for the first time that I could remember. And I actually met an amputee for the first time during that trip, and she was actually my age, 7 years old, hobbling towards me using a broken tree branch as a crutch. And at the time, I had wondered, we have the same ethnic heritage, but we have such vastly different qualities of life. And as I grew older, I began to realize that, this wasn't her fault necessarily, but rather a lack of resources, be it healthcare, be it security, be it financial resources. And that kind of gave me the inspiration to want to build these prosthetic devices, especially in developing nations. Because it turns out that there are 11.4 million hand amputees around the world, and around 80% of them come from developing nations. Of that 80%, less than 3% have access to affordable rehabilitative care. And the current prostheses that are out there right now, so you can see basically the two types of upper limb prosthetics on this man right here. On his right hand, you see a hook, right? So the way this works is that he has a bicycle cable that goes from his hook to his shoulders, and when he squeezes his shoulders together, the hook opens, and when he relaxes them, the hook closes. So it's a pretty robust device, but it only offers you 1 degree of freedom. All you can do is open and close the hook, and it's not necessarily very intuitive to control. You have to move your shoulders in order to make this hand open and close. But it costs around $500. Now, the hand on the left is what's known as a myoelectric prosthesis. So this myoelectric prosthesis is controlled by sensors that are placed on the residual muscles of the user. So whenever he flexes his residual muscles after the amputation, those signals will be picked up by these sensors, and then he can use it to drive those prostheses. The vast majority of them still only open and close, but it's a lot more intuitive. He thinks about closing the hand, and it'll close. He thinks about opening the hand, it'll open. However, that hand in particular costs around $15,000, and the state-of-the-art ones that are like the best of the best that you can get cost around $30,000 to $40,000. Now, that's after markup and all of that stuff, and in material costs, we're really thinking about $5,000 to $8,000. But if we're really thinking about the 80% of the people in developing nations who need prostheses, still, that is a very, very high cost. So our solution is a very simplified design that we can make these prostheses at 1/10 of the cost. And this is one of our latest prototypes of our prosthetic hand. This is 3D printed in our lab. And it can do many of the functions that the state-of-the-art prosthetics can do. So for example, we're going to make it do a power grasp, right? So this can be connected to an amputee, and when he thinks about making this grasp, it'll actually do that. We'll open it back up. It can do like a 3-finger grasp, so that's for more precision. And also, if we want even more precision, like a fine pinch if you're grasping very delicate objects. And so all the electronics and all the material costs for making this particular hand is only around $270. So huge price difference. And yes, it's 3D printed, so there's some drawbacks with 3D printing. However, we'll address some of this new stuff that we're working on as we get towards the end of the talk, which makes this a lot more robust and viable in developing nation environments. So secondly, we use neural muscle pattern recognition technology. So remember how I said that even that $15,000 prosthetic hand that uses the muscle sensors, all it can do is open and close? So we employ machine learning algorithms that allow the user to do more. So this is a video of what the signal looks like.
Here's flexion, here's extension, flexion, extension. Signal to noise ratio is awesome, and it's working. Here's squeeze, you can see them both.
So what we can do is we can place an array of these sensors around my forearm and then capture all the different grasps that I can do, because it turns out that all the muscles that control flexion and extension in your fingers, they're located in your forearm. So we can actually, when I do a pinch, we'll get different muscle patterns activities. When I do a 3-finger grasp, different sets of muscles will be firing. We have a machine learning algorithm that can actually learn those different grasps. And then finally, we're the only hand that has touch and joint location sensory feedback. And so this is a huge problem for amputees specifically. So if I were to if I lost my arm and I closed my eyes and I tried to move my fingers around, if I was fitted with this prosthetic device, with any prosthetic device, I actually wouldn't know where my fingers are without having to look at them. And that's a huge problem because, right now I can actually point to them with my eyes closed, right? So because of that, it leads to people not using their prosthetic device at all in favor of their intact limb. And also, if they try to touch a surface with their prosthetic device, they can't feel it at all. So we're actually able to give both of those sensations back to the user, and we'll talk about in the second half of the talk exactly how we do that. So we started building our own prosthetic hands in the lab about 2 years ago now. And this was one of the very first ones that was designed. Now, the problem with using this particular design for a prosthetic limb is that all the motors are actually located in the forearm, right? So if you still have your forearm, you can't place motors there. So we had to come up with a new solution that had all the motors inside the hand. But let's back up a little bit. So I would say about April of 2014. This is David Krupa. He's an alumnus from the U of I. He co-founded this nonprofit organization known as the Range of Motion Project. And their whole goal is to provide a more equitable distribution of prosthetics to those who need them around the world. And they're based out of Guatemala and Ecuador. And so he was coming back to the university to give a talk, and I think he had won an International Humanitarian Award. And so the thing is, at U of I, talks on prosthetics are few and far between, so I had to go talk to him and tell him that, hey, we're 3D printing our prosthetics in the lab. Can we do anything with that? And so a couple of weeks later, he sent me an email saying, dude, I just got this vibe from you, and I think it would be awesome if we could collaborate together on a 3D printed hand project. And so another week later, he said that he secured funding from the U.S. Embassy to send 2 of us down to Ecuador to actually use this prosthetic hand on a patient. So this was a long time ago before we had this guy. And we hadn't actually put all the motors inside the hand yet. So we had about 2 months to get all the motors in the hand, get all the pattern recognition with the EMG working, and then have it work on a patient, which we've never done before, right? So the day before we get down to Ecuador, we don't really have the hand working, but we have all the pieces there to kind of like get it working when we get down to Ecuador, right? So we land, and then Dave tells us, oh, we have a meeting with the U.S. Embassy the next day, and they want to see the hand working. So we had our work cut out for us. In the 2 weeks we were there, it was basically one long all-nighter. And the first night we were there, this is our initial test. So we barely got it functioning to the point where if I flexed my hand really, really, really hard, the hand would close. And if I extended my wrist really, really hard, the hand would open. And so this was one of our first tests in grasping a bottle.
Yeah? Okay. Are you recording or not yet?
I am.
Okay, so clearly Unfortunately, maybe the diameter of the Powerade bottle was a little too wide, so we decided to, maybe we should switch to something with a little bit smaller of a diameter. Still, we had some issues. So we tried again. Finally, we had success in grasping this bottle. And so we brought this to the U.S. Embassy, and the thing is, that was the first time they'd ever seen a robot in their life, so just seeing something move was just floored them, right? And as soon as they saw that, then they started talking about, okay, now let's talk about media coverage, right? So we're thinking like 2 news stations, 3 newspapers next week when you get this working on an amputee. And we were like, okay, that's a lot of pressure. And then they asked us where we were from, and so we were like, oh, we're from the University of Illinois. And then they were like, oh, you guys are from the University of Illinois. In that case, we're going to bump you up to all the national media stations. Because it turns out that the president of Ecuador is an alumnus of the University of Illinois. And any chance he gets to promote the university, he takes it. So in the next couple days, we met our patient. This is Juan Suquillo. He had lost his arm, or his left hand, 30 years prior in a border skirmish between Ecuador and Peru. And so this was one of the first times that we had hooked him up to the device, and we could barely get it functional. It wasn't working very well. Well, what made matters a little bit worse was that the following day, he was flying out to Brazil, and he wouldn't be back until the day the media came. So that meant that we had basically one shot to get this right when he comes, and we've got to figure out everything that's been wrong with this device for like that week. So let's fast forward to the day the media comes, right? So it's 6 a.m. The media's coming at 9 a.m. on the following Thursday, right? So this is that Thursday now. And we had been up for about 36 hours straight at this point, just trying to get this hand to work, right? And so basically what I was trying to do is I was trying to like do a pinch and make the hand would pinch. I was trying to do a 3-finger grasp. The hand would respond accordingly, and it just was not working. And the night before, Dave Krupa told us that he was going to come pick us up at 6 o'clock, and whatever we've got at that point, we just have to work with it. And so 6 a.m. rolls around, and we don't have it working. And I don't get a text from Dave Krupa at all yet, but I'm just feverishly like looking at this code. And then I see something that seems a little bit quizzical, a little bit off, right? And so I text Dave Krupa around 6:06 saying, I think I might have figured it out. And it was one line of code where the variables were switched on the opposite side of an equal sign. Once I swapped that, everything started working. And now when I made a pinch, it made a pinch, etc. And I was like, oh my gosh, if he came at 6 o'clock on time, we would have been screwed. But it's one thing for it to work on me. It's another thing to get it to work on the patient. So we're thinking that, you know, if he gets there a little bit early, we can test it out on him and everything will work out just fine. 9 a.m. rolls around. All the media is there, but he's not there. And so he gets there around 10. So now we really have one shot to get it right. We hook all the EMG sensors, the muscle sensors, up to him, look at the signals, and they are all dead. Not a single muscle signal was firing properly. So now we go into debug mode while Dave Krupa is trying to stall with the media and tell the story of like the range of motion project and Juan. And we check, and so we check the voltage, and usually if there's a problem with the voltage, that means there's a problem with the power supply. So we looked at the battery. The battery was pretty swollen, and we touched it, and it was super hot. And you know, had we not caught this earlier, we would have been on the news for something else. And so we quickly unhooked the battery, swapped in a new one. Poof! All the EMG signals were showing up just fine. And it was like awesome. And so now it was time for him to like actually test the device, train with the device. So you undergo like a 30-second training process where you'll teach the machine learning algorithm like the muscle signals corresponding to pinch, 3-finger grasp, hand close, hand open, and rest. So he goes through this process, and then the hand will open. It's ready for him to control. So he goes to close the hand, and nothing happens. So we're like, not again. And it turns out that Juan Suquillo is the leader of all the Muslims in Ecuador, and I happen to be Muslim myself. And so he looks at me and he's like, Bismillah, say Bismillah. And for those of you who don't know, Bismillah is what Muslims say. It's just invoking the name of God, and you're supposed to say that before you start anything, right? And so I'm like, okay, Bismillah, Bismillah, right? And then I reset the device. He goes through the training process. The hand opens up. This time he tries to close it, and it responds. And I would just look at it, and I'm thinking in my head, you are a man of God. And so this is a video of one of the...
Un quiteño es el primer beneficiado de una prótesis de mano con ayuda en su financiamiento. El programa es realizado por jóvenes de la Universidad de Illinois en Estados Unidos.
Juan Suquillo es excomandante de guerra. Fue así como perdió parte de su brazo. De esto han pasado más de 30 años.
Varios miembros de mi pelotón sufrieron heridas y particularmente la mía me cobró el brazo izquierdo.
Gracias al avance de la tecnología, hoy puede acceder a una prótesis.
Parte de mí ha vuelto.
Jóvenes ingeniosos y con un gran empeño por ayudar al prójimo más necesitado han desarrollado una prótesis de brazo mioeléctrico con la posibilidad de retroalimentación sensorial, es decir, sentir como una mano de verdad.
So what I really wanted to highlight there was the fact that he said that it felt like a part of him has come back. He was doing motions with his hand that he hasn't been able to do for the last 30 years, so that had been really powerful for us. But he hasn't even tried any of the new sensory feedback stuff that we're going to be bringing down in a month. And so that kind of segues into some of the sensory feedback aspect, closing the loop on these prosthetic devices. So I was talking about how commercial myoelectric prostheses lack proprioception. If you close your eyes, you don't know where your fingers are, right? So we devised a very simple way of giving this back to the user that's very low cost. So this was that first prosthetic hand that we had. And we 3D printed these contact pads. They're about the size of a quarter. And we just tape those down to your skin. And they're connected via a wire to the motors that control the joints. So now, when the motor turns the wire connecting to the joint, it'll simultaneously tug on your skin. So that way you'll know where your finger is located by the amount of skin stretch you feel and how fast your finger is moving by the dynamics of that skin stretch. And it's nice because it takes up a small surface area. It's basically adds very little power consumption, and it's can be added to any prosthesis device. So just to give you an idea of how it actually looks. So as this finger moves through that, this kind of like stretch the skin. And so we did an experiment where they had to identify these 6 different graphs just based on the skin stretch feeling alone. And what we found was that after 6 minutes of training, we blindfolded them and put earmuffs on them. They were able to identify those graphs with over 88% accuracy. And now imagine if they were doing this for weeks to months, how good they would be at recognizing those different graphs. And also, they could target different grasp apertures, like different closing degrees, but within 10 degrees, which is also very profound for this type of feedback. Now, in terms of touch feedback, the way we do it is there's a barometric pressure sensor that we have in our fingertip, and then we will take that pressure and then feed it to the user via electrical stimulation. So the same sensors that are on the muscles to record your voltages, we'll instead send current through them, and you'll actually be able to feel something. So if I could have a volunteer from the audience to actually try it out, you can actually feel what the finger is going to feel like. Does anyone want to try it? All right. And I will just switch over to LabVIEW really quick. All right, so go ahead and come over here. And so this is the same fingertip that's in that prosthetic hand over there, but this has that barometric pressure sensor that was in there from before. And so what I'm going to do is go ahead and give me your forearm. So the idea here is that if he lost his hand here, we would actually put the sensors here so he'll actually be able to feel something. tried electrical stimulation before? Okay. So as this loads, basically what we're going to do is we're first going to find what your minimum and maximum amount of sensation is going to be. Okay, so we're going to start to slowly increase the voltage or the amount of current that you're feeling, and then I want you to tell me as soon as you start to feel it. Okay? It'll feel like a light tingling or a vibration. It should be. Do you feel anything yet? What does it feel like?
It's like, you know when you numb your fingers?
Yeah, okay, yeah. And so if I do this, is it gone?
It's the same.
Just give me 1 second. Oh, well, the box stopped working, so that's unfortunate. But you can always come back to my office. But the pressure sensor is working. So this is the pressure sensor in here. It costs around $5, and it's very responsive. And so you would actually be able to feel that pressure if the stim box was on, which I'm not sure why I tested it right before this, but that's okay. So basically, we are now forming a startup out of this called Psionic, where we actually give this feedback back to the users. And we actually tried it out on a patient, and he said that this was something that he would use on a daily basis because when he was first fitted with his prosthetic device, he ended up crushing his grandmother's hand when he was shaking it because he couldn't feel any force feedback. So with that, I'd like to conclude my talk, and thank you, everyone.